Good afternoon. We are going to talk today about trusted execution environments, and here is a brief outline. So, before we begin trusted execution environment, I wanted to give little bit of recap why we want a trusted environment. And the way you want to visualize is that when you consider data, any data, when you consider data, data could be in three possible state, either it is on rest, which is basically in the storage or in memory, or it could be in transit. So, it is moving from, for example, main memory to cache or one processor to another processor, or it could be in use. So, think of data is getting used in the ALU for computation. Now, when we talk about data, I am not distinguishing anymore between instruction and all that, any form of values, right. Now, when you look at these data of three usages, the encryption actually works very well for data at rest or data in transit, because that is where it is used. You encrypt the data, this could be an email, this could be your program, you encrypt it and that is in stored. Then same thing about in transit, two parties communicating. Remember when we talked about encryption, the sender basically will encrypt the message, and then that travels the encrypted one, and then recipient will decrypt the message, whatever message was sent, depending on whether it is a symmetric cryptography, asymmetric cryptography, that is the model. Same thing in the rest, you encrypt the data, you keep it, that is kind of secure. But data in use, encryption will not work unless you use something called homomorphic encryption. And those of you who are following the domain of homomorphic encryption, idea is very cute, and basically the idea is, if you have two sets of data, so the idea of homomorphic encryption is basically is that if you have a data A and data B, and you cannot compute that data in your own computer, you are sending to the cloud or any untrusted party, you do not want people to know your data for privacy reason, copyright reason, whatever it is. So, you basically send the encrypted version of A, encrypted version of B. Remember, A and B may not be a variable, it could be array, it could be a truckload of data. Now, when you send it to the cloud, this is you send all of these data to the cloud, this could be cloud or cloud provider, where they are probably doing just addition for you, addition, average, whatever, really does not matter. So, what they will do, EA plus EB, and then they will send you the result back. If you follow exact homomorphic encryption, when the data comes back, this EA plus EB, when they compute what they are really send, when you decrypt it, this EA plus EB result, if you decrypt that whatever comes in, you will actually get A plus B. So, that means homomorphic encryption allows you to perform operation on the encrypted data, you do not have to decrypt it. Now, this idea is kind of many design automation company CEOs, if you talk to them, they say, oh yeah, no, our tool takes encrypted net list and do the synthesis. That is not true. What they claim as encrypted net list, when it comes in VHDL Verilog code, they want to do synthesis or compilation. Internally it decrypts it, then does synthesis, and then encrypts the synthesized design and then sends you back. So, that is actually not homomorphic encryption, so that you understand. But from customer side, customer may feel comfortable listening that company X provides tools that operates on encrypted data. This homomorphic encryption idea is mathematically guaranteed, and addition subtraction is fine. People are talking about machine learning using homomorphic encryption, and machine learning has all these multiplication and all that. Those are very expensive, very slow, and really resource intensive. Most of the work in homomorphic encryption community, how do we do homomorphic encryption which is not 10 times slower than the actual computation, or any machine learning that we are doing, performing machine learning. Training is one thing, but when it is operating also on a regular environment, if it is 10 times 5 times slower, then that is not what I want to live with. That is not a real time kind of story. So, most of the work in this area, until that story becomes real, then we are going to stay with the trusted execution environment. Trusted execution environment provides you the confidentiality in all across the spectrum, data at rest, data in transit, data in use, and in addition it provides some other stuff which homomorphic encryption or nobody else provides, such as integrity, availability, attestability. I will get into those details. Can anybody tell me why I explained all this stuff? I am trying to sell trusted execution environment to you and why you would buy, because if your first reaction would have been, oh, I can encrypt it. If confidentiality was your only target, it would still work, but it will not work for this. Homomorphic encryption, except the people who are working in homomorphic encryption, nobody believes today we can use it any real time, safety critical or any of those systems where if time is a non-issue, homomorphic encryption is fine. We already have mathematical technology to basically perform computation on encrypted data, perform machine learning on encrypted data, or even more interesting, the machine learning model itself is encrypted. Encrypted machine learning model will make the decisions for you. Any questions? So, as I said, the objective of trusted execution environment is to give data confidentiality, data integrity and code integrity. By the way, this data confidentiality also takes care of code confidentiality. In layman terms, I wanted to draw something that everybody can understand. Hardware, or at least some part of the hardware, we have a dedicated day on just cryptographic modules, that is assumed to be secure. We call it root of trust, and I have one whole day dedicated to talk about or zoom into root of trust. How do we design, how do you attack, how do you mitigate. Once you have a root of trust, then basically on top of it you have the application layer, where you have operating system and different applications or programs that you are running, that is running. But trusted execution environment makes this partition, logical partition. Anything, this trusted OS component, any program running on top of it or anybody running within that enclave is basically assumed to be secure. So, not only, so who are the other people who are trying to, what is the threat model? Threat model is anybody running on the normal operating system. Now, remember, this could be two operating system, this could be same operating system, and let me do one little layman term. So, if this is your hardware, this is your hardware, which basically your processor, cache, whatever we talked about in microarchitectural attack, your processor, cache, cryptographic modules, all that. On top of it, you have your operating system. On top of it, depending on how things are, in multiple user and all that, you have different programs running, application 1 or program 1, program 2, program 3, they are running. Now, at this point, let us say application 1 is basically malware detection, secure algorithm. You do not want other application to kind of interfere with this operation. The way trusted execution environment handles it, think of hardware has two processor core, processor P1 and processor P2, and then of course, there is a little bit of memory issue also. So, what it tries to do, it basically creates a logical, that is why it is called enclave, a logical enclave or boundary, think of a brick wall around it, so that all other applications that are running, they cannot interfere with A1, but A1 can interfere with them if needed. A1 can monitor what A2 is doing, what A3 is doing. So, it is not just processor P1, it is little bit of cache, some part of the cache, some part of the main memory. So, think of all the hardware, some part is typically it is 10% of the hardware. The enclave can kind of give protection, a software layer through a set of instructions, or we call it privilege instruction. Through those instructions, I will zoom into all of that, so that you know how is this built. And that boundary idea is, if anybody tried to access that boundary, so this application may be directly trying to know this, or through operating system, or through hardware, processor, any side channel, all of them should be declined, cancelled, blocked. That is the idea of trusted execution enclave. Anybody inside the enclave, they are supposed to respect each other, but the boundary kind of is not that strict. Anybody inside or outside, boundary is lot more stricter. Page accesses, memory accesses, who is doing this is additional layer of check in addition to what operating system does. Security enclave such as Intel SGX, I will zoom in little bit of that. They company quickly figured out this is simply too much, too many bugs coming out, too many vulnerabilities, too expensive. So, later they moved from the security enclave concept, all companies actually moved now to virtual machine based TE, VM based TE, and the basic difference is it relies on the based on the VM or virtual machine. Let me just spell it out, because we are using VM. In the previous lecture we talked about VM as virtual memory, which is basically virtual address space, but now we are saying virtual machine. Idea is slightly different. Let me do a quick 1 minute recap. Virtual, and the idea is the difference you will be able to see if this is your hardware, CPU, memory, all that stuff. If this is your hardware, on top of it you have a tiny layer of virtual machine monitor. Think of operating system is buggy and big, too many vulnerabilities no matter how many you fix. Think of VMM is the thinnest layer of that operating system, the bare minimum code that you can verify very confidently, view that way. It also does few other things. On top of it you can install something called virtual machine. This could be one virtual machine, this could be virtual machine 2, and on top of it applications will run, maybe application 1 running there, application 2 running there. So, idea of the virtual machine, as the name suggests, as if it is a computer by itself. So, when you talked about virtual memory, we said every program has a feeling I have the whole memory space. Virtual machine is even worse, it basically makes an assumption I have everything. So, a virtual machine, think of it, this could be a Linux, in reality this could be a Linux operating system, this could be an Windows operating system, and this could be one of the VMM that is publicly available. So, in reality on a single machine you can install multiple operating system. You do not have to, if you are delivering a software to your customer, you do not have to go room to room, take a USB out from this machine, log into another type machine. On the same machine you will be able to install different operating system. So, managing software, managing hardware, all that becomes the easier. But this is the notion of virtual machines, and in this virtual machine if the VM is trustworthy, this VM is trustworthy, it will not allow anybody to do hanky panky, any other VM to do hanky panky with this one. As we go forward you will see I will also relax that assumption. If this was a trusted VM, it does not matter what else is where everywhere, it would still work. So, because this concept is new, I am waiting for you to ask me any question. Virtual machines. So, this is non-virtual machine, normal computing environment. Yes, please.
Sir, like the virtual machines off the shelf such as the Oracle virtual VMware that we get, so that we install on the operating system.
So, that is what I am saying, this VM is actually the operating system from the hardware side, but in a thinner layer. This is the operating system from the application side. So, this operating system thinks I have the access of full hardware, but that is not true. This operating system, this is also known as host OS, this is known as guest OS. See, this host operating system actually there could be multiple VMs running. So, it basically shares this resource among those VMs. Exact analogy here, this operating system, every application think I have the full access of all memory, actually not just 2 to the power 50, they have a feeling they have 2 to the power 64 of the memory space, more than what is in reality. So, each application has feeling I have access to everything, and operating system is a single one. Here every operating system, first of all each application think I have access to everything, but that expectation ends right here, and then this operating system has I have access to everything, which is also not true, because the total memory space is constant. So, the memory space divided between different VMs and that is further divided between different application is different. And in fact, when you do a page mapping or virtual to physical translation addressed. So, virtual memory on top of VM would be you are doing address translation, virtual address translation to physical address. I am calling it physical address prime, because this operating system thinks I gave you a physical address, but that is actually not a physical address, that is something in between address. That is why in this community this address is called physical address and actual address is called machine address, which is real. This is like fake real, this is real, this is really fake. So, there are everything has a multi-layer translation. You make a single call to print in the screen see out or something, it would have 2 calls. You have an exception branch misprediction, it would have at least 2, could be multiple, because this operating system thinks I am the boss, this operating system is actually the boss, and all of this story. Now, how does trusted execution environment works? The easiest way to implement would be this, but it is not implemented as an enclave after understanding all the problems of enclave. This is implemented actually much easier way. The key idea is, if you are a trusted party, you request me an ID, I will give you an ID, and next time you run your operations I will check that ID. So, basically I am just ensuring if you register the ID, and I will make sure you just within yourself. So, it is a very much simpler assumption, and as I said, if VM is trusted, this problem is actually trivial. VM actually takes care of the security issues, but later I will show that VM is also not trustworthy, or that is a threat model. Any questions on this one? So, we went for normal computing and trusted execution environment. Out of multiple cores, little bit of core, little bit of memory is dedicated to a set of applications, and somehow a part of the operating system or a set of instructions in the security enclave takes care of it, just to make sure nobody, whatever memory, let us say if this is your cache part, your locations 0 to let us say 9, let us say 0 to 4 was given to you. So, extra checks would be checking that if anybody trying to access any of these locations, are these locations legitimately for the applications which has legitimate access to the security enclave. So, most of the attack on security enclave, there are various types of attack. So, and some of those attacks I did not talk about, because I focused on cache timing attack. So, one VM trying to attack another VM, that is a very common attack in the microarchitectural domain. So, trusted execution environment basically takes care of it, and this one VM trying to attack another VM again comes from the same effect. Operating system is a millions of line of code, if not hundreds of thousands of lines of code, and verifying all of them or guaranteeing all of their correctness is impossible. So, there are so many vulnerabilities, people just kind of figured out that vulnerabilities and exploit that vulnerabilities to mount an attack. Now, I come back to this. So, basically this is the key idea, whether it is the VM based story or non VM based story, there is a partition, logical partition, no physical, logical partition, we and them. We are great people, secure people, trustworthy people, respected people in the community, and they are blah, right. Any question on this? Of course, you remember by definition of OS, even they are untrusted, it is not that this particular application can access the memory of this particular application, this is also still not allowed. But as you saw in the microarchitectural attack, that is possible, but trusted execution environment basically trying to block this story, that this application somehow directly indirectly trying to get something from here, that is prohibited.
So, can we have the same Spectre meltdown attack here as well?
So, the answer is yes, you can attempt, but the way Spectre meltdown attack works, this would be kind of this security 10%, this cache flushing and all that, this is the inherent part of it, it will not even allow that to happen. Now, the reason things become complicated, that is basically our wish world, what in layman terms what should have been the trusted execution environment, but in reality as you can see, even in the operating system many components, I just try to divide in different components, this does not represent any company, later I will zoom in, you will see different company how it behaves, but in different companies implementation of trusted execution environment, different part of the components are potentially untrusted. Here green is trusted and maroon or brown is basically potentially untrusted. So, of course, you need little bit of trusted hardware. If the hardware itself is unreliable, then it is basically everything down the drain. Little bit of firmware has to be trusted. So, within that even BIOS could be untrusted, device driver could be untrusted, hypervisor could be untrusted, cloud management could be untrusted, and of course, there are lot of untrusted VM and untrusted different devices you connect like USB stick and all that. So, within that then how do you guarantee when you provide a trusted execution environment in such a model, how do you kind of guarantee that that trusted execution environment is trustworthy? That is what I am going to delve in. Any questions on the reality of where we stand today? You have lot of components in this full stack. This is where your program is running, this is your processor, and in between there are so much of software layer, and in the software layer what you are saying, even some of, so technically speaking this is your virtual machine monitor, or what you mentioned as this is your host operating system. Even the host operating system is untrusted, that may have vulnerability, that may have malicious implants in it. And device driver, just to give a layman's view. So, when you print anything from your, this is your CPU and you want to send a request to a printer, wherever it is the printer, there needs to be a device driver that basically takes the request or the pages of data and print it. That is why when you buy a new printer and you want to connect to your computer, you have to install the device driver of that computer, right. So, then technically speaking you have the hardware and then you have the operating system, and there are many models, but in different models some models device driver would be on top of OS, some model device driver would be here, some model device driver could be even below here, but whatever it is, from different IO devices you need a device driver. From that device perspective, that is the operating system. For that printer, that is nothing but operating system. In fact, the USB stick when you plug in, that is also has a device driver. It is just that luckily we do not have to install a device driver for what type of USB stick we put in, because it is part of standard PCI kind of protocol, peripheral component interface. There is a standardization, because everybody has to follow that standardization. That is why you plug in USB, everybody kind of pulls it up. So, how many trusted execution environment exists in reality? There are actually many. So, if you look at the industrial context, so AMD secure encrypted virtualization, they have many variation. Intel SGX, as I said, it was security enclave based, which is pretty much not used today. Intel Trust Domain Extension, new Intel machines coming out. So, if you buy those I do not know $5,000 to $10,000 AMD machines, then you will find that one, some of the latest Intel machine you will find TDX, but the older one you may still have SGX. IBM has a secure execution, ARM has trust zone. Now, all the researchers basically work on these and these. IBM never released their environment. IBM does not believe in academicians trying to find vulnerability and they will fix it. They have a different model. Lot of legacy system, large enterprise systems run on secure execution. So, it is not open for research. So, ARM trust zone, embedded mostly embedded domain, ARM and RISC-V, and these are mostly for general purpose domain. And there are many academic exercises, MIT Sanctum. So, it is basically tried to improve SGX with lot of extra instruction, think about it, just to close the vulnerability. And then there are academic version of OPTE, which are based on kind of ARM trust zone. Then there are for embedded systems, Keystone, Trusty, and there are many for Android devices, even for devices as small as form factor of smartphones. I just tried to put them in perspective. So, most of the today's ones are Intel TDX, AMD SCP, they are based on virtual machine based TE, and the things of yesterday was Intel SGX, Sanctums and so on, those are enclave based TE, much stricter requirement, lot of performance overhead, and yet lot of vulnerabilities. and then there are TEs that are kind of for resource constraint systems. I will try to zoom into each of them to give you a flavor, keystone, multi-zone, and most of these TEs, or at least the one I will talk about, these are kind of either RISC-V based or kind of ARM based, and these are Intel TDX and SCP, these are Intel and AMD processors, and as I said, these will not focus that much. Any questions? So, what we are going to do, talk about when you have such systems, how do you kind of verify their trustworthiness? That is what I am trying to kind of zoom in, right. So, first thing so let me just kind of go into the flow. When you have a trusted execution system, it is very important to decompose them. Why do you want to decompose? Because if you go back, this is basically the real world story. Recall we talked about that even verifying hardware is impossible, verifying operating system is impossible, but for proving that your trusted execution environment works, we have to kind of guarantee that when this VM makes a call, it get routed by this hypervisor through firmware or not to the hardware, and the way request comes back through the hypervisor. So, multiple parties of hardware, software, firmware gets involved. In addition to cache talking to main memory, somebody talking to somebody, many parties get involved. So, if you want to do a standard verification, that is not going to work, because remember, even verifying standard CPU itself is impossible. We are trying to do abstraction and all that. So, therefore, if you want to verify anything, we need to somehow break into subsystems. Who is talking to whom? Can I kind of cover this part of the story? Can I cover this part of the story? And you still have to guarantee when you break them in pieces, collectively they still give you system level guarantee. So, this is basically then you kind of do the decomposition, then you have the secure subsystems. Once you have the secure subsystems, then you kind of generate the corresponding properties or behavior you want to check, and then you kind of check those behavior. That is kind of one way of looking into it. So, when you talk about decomposition, this diagram itself is a layer of decomposition. So, there is a hardware layer, firmware layer, BIOS layer. So, this is a horizontal decomposition. I will also talk about vertical decomposition. So, when you look at the AMD SCV, also I did not get into the detail, but I will still have to kind of wanted to show you this firmware. In the previous diagram you saw the firmware, this hypervisor is same. So, guest, so the notion of guest and host is this one. So, this hypervisor is kind of the host, this is kind of a guest, this is a guest virtual machine, also known as guest operating system 1, guest operating system 2, and these are of course the guest applications. So, that is the notion of guest. Or so, on the guest side, certain set of transformations are valid, and that is defined, and hypervisor basically looks into that, and then basically when it kind of, remember, hypervisor is not trusted. So, therefore, although there are transactions happening through hypervisor, you still want to make sure in the system level when multiple parties goes through hypervisor. Who are the multiple parties? This application is going through this hypervisor, this application is also going through this hypervisor, of course via this VM. While this hypervisor is untrusted, it should not happen, some information coming through here should not be routed here in any manner. That is the whole in spite of hypervisor being untrusted. So, the way transitions are, and as you can see, most of the names, it is all about pages, page transfer between the translation look aside buffer, fake translation look aside buffer here, real translation look aside buffer that maintains the page mapping of virtual addresses and physical addresses. Those mapping, those accesses, who is accessing whom. So, most of them at the top layer, once you zoom in, each of the one you click, it is going to bring another finite state machine. Once you zoom in, it goes down all the way to accessing bits and bytes, but basically who can access which page and which page access should be denied, move, reclaim, update, swap in, swap out, all that is basically transformed. And the reason I am showing, so identifying that finite state machine, identifying this the transitions, That is really the context. Now, where does all the why this is so important, because when you try to verify trusted execution environment as a researcher, you do not have access to the source code of the designer. AMD is not going to give you the source code, only thing you have access their English document. From that document you need to kind of figure out this. What else you have access? If you bought those high end machines, you have the access of that machine, where you can actually compute and execute all of that. If you really want to mount an attack, whether to prove it is correct or whether to prove there is a vulnerability, you have to set up pages in a way, you have to do attack victim process in a way where you can claim or get information from a process within the trusted environment. That is basically the story. So, Intel SGX it is basically based on the security enclave, and it's kind of you initialize certain edges, or you kind of use, not use, allow somebody, resume, exit. It is kind of the idea of creating pages and marking a page for somebody and making sure whoever is accessing the page, it belongs to them. And of course, all the attacks on SGS basically violates that premise in two ways. One is, if I can fake that I am inside the enclave, then I basically got that benefit. So, an outsider, remember it is we versus them. So, one of them suddenly become part of our core group and kind of pretend in a manner or change the ID, change the authentication in a manner to show I am a legitimate user or that is my page, then you basically get access. Most of the attacks are that way. Now, TDX, which is basically kind of based on virtual machine, and remember the key idea here is virtual machine monitor is kind of untrusted, and the way I wanted to show as if there is a brick wall right between the trusted VM and untrusted VM. Although the calls are getting routed, although it is technically not correct, the way you want to visualize all these data that is coming, this is trusted VM. When it sends some data, think of that say encrypted data, which is not true. That is encrypted data, it comes in and decryption happens somehow in the trust domain in the trusted VM space. That is the way to visualize, that is the way to visualize break, but actually it is implemented in a much easier way. You request access, then you create an entry, and when next time request come in, it basically checks does it resolve to your access. If you zoom in further, this ID, whatever this ID and this trust domain, so this term should be familiar to you, is flashing. It basically flashes the TLB and then basically it creates, assigns, and whenever it is not needed anymore, it tears it down, right. And then when it configures, it is uninitialized, initialized, runnable. This is where it get access. First of all, this trust domain for each of the trusted virtual machines or the applications that running for on a different page basis, right. It is basically creating, adding, initializing and maintaining all of those in a table in a manner that is local to the trust domain. So, again all of these are maintained per basis, and when I talk about properties, you will see basically we are checking, is it possible for another application to pretend that I am the legitimate user of this trust domain. So, that is basically the idea of TDS, trust domain extension. So, the idea is the trust domain, either you are either me, you registered with me, or you are not registered with me, and just ensuring that kind of access happens. So, once you kind of have this decomposition, who is talking to whom, when you talk about property generation, when you have all these subsystems, who is talking to whom and how they are, then these are the type of properties. This should be obvious, because that we need to do confidentiality and integrity. In addition to that, it also provides availability, attestability and so on to generate those. So, confidentiality, if you recall, confidentiality between two parties, sender and recipient. So, confidentiality basically means when you communicate and send a message, nobody else should be able to understand the message, even if they are sitting in the middle and trying to figure it out, they should not be able to figure out, right. That is the confidentiality. And in a normal world without trusted execution, it is implemented through encryption. and the integrity basically means now that I could not understand what it is, can I modify this message, and I want to modify in a manner so that when sender sends to the receiver, receiver does not think this is a fake or scammed or modified message. So, some of the normal techniques during communication people use like parity or checksum, let us say even parity. So, then you cannot change one bit, you have to change 2 bit. If you are changing one of the 1 to 1 to 0, then you have to change another 1 to 0 to 1 or something, you have to change 2 of them, whatever it is. So, that is basically integrity. If you just randomly change bunch of bits, when decryption happens at the receiver end, receiver will figure out this does not make sense, that means somebody did the violation. So, that is not an integrity property, but either way. So, when we look at this subsystem, our key idea is, do we know is confidentiality maintained or broken, do we know if integrity maintained or broken, right. And how would this, I will show you how those are checked, but how would the properties look like for confidentiality, integrity? I will talk about in a moment how do you generate them automatically. They will look like hypervisor implement. So, E, so this is a temporal logic. E basically means there exists, so it came from the word exists. There exists a scenario where hypervisor implements implies that not read private VM memory. So, the hypervisor, if the person who is requesting access, if it is a hypervisor, it should not be able to read my memory. So, similarly different. So, for example, this is even easier. If it is an unauthorized user, of course, nobody will say I am an unauthorized user, right. If it is an unauthorized user, then we should not allow code access to certain components. And and then if write page we are allowing, then user has to be the owner of that page. So, this is the integrity part. If somebody is modifying something, it has to be the owner, and this particular one is basically saying nobody else can access it. So, availability basically have similar thing, attestability has similar stuff. Now, how do you generate these properties? So, basically this is where machine learning comes very handy, at least large language models. So, initial experience was, so first of all let me talk about the flow, then I will come into large language model. Remember, the specification is an English document. From an English document you have to construct those finite state machines, and that is not an easy task. Reading English document, drawing those finite state machine, who is talking to whom to make any guarantees, it is not an easy part. And assuming you have the finite state machine, then based on the template I will show in a moment how the temporal logic property look like, we can generate the property. We can traverse this finite state machine in a manner, and then we kind of try to pose the property what should hold true or what should not hold true. So, the way, and then once you have the property you can do property checking on the implementation. Now, for Intel TDX an implementable C code version is available for the TDX. For other computers you have to run that on the real system, real hardware if you have access to, because nobody will give you VHDL Verilog code, right. So, let me just briefly talk about this FSM extraction. So, right now the story is manual, there are a lot of work and effort going on. How do you generate these FSMs automatically? So, initial experience with some earlier ChatGPT, it produces bunch of garbage. Then you have to keep on guiding, oh start with a start state, okay, whatever they generate then they call that one start. So, pretty much you have to just, you exactly know what FSM should look like, you have to keep giving those verbal instruction, then it will construct. So, that is more painful than drawing by yourself, but the recent version of those ChatGPTs with billions of things, they actually do an amazing job that would surprise you. They pretty much except one or two state or one or two transition, they pretty much you give 100 pages of document, it will bring up the FSM correctly. They do an amazing job. Now, so how do the, so when it construct FSM, how do those FSMs look like? Again, you need to give little bit of guidance or prompt engineering. And so, for example, this prompt engineering on TDX, it created two finite state machine. One is on key management, another is on trust domain life cycle, and how those two finite state machines interact with each other. Once you have the finite state machines, then it is actually the template do the trick. So, the template is, before I talk about the template, let me talk about what these things be. Confidentiality and integrity you already know, those are very specific to trusted execution environment. In addition to that, these safety or liveness, these are classical expected behavior we want for any design, not just trusted execution environment. And safety basically says that some safety checking is basically some scenario that you do not want to happen, right. Liveness means something you want to happen for the lifetime, something to hold for the lifetime, that is why the name is liveness. So, if a car is waiting, it would get let us say access of a green light. So, that is kind of a different behavior versus both sides should not be green at the same time, that is a different kind of behavior. And here safety property means if certain event happened, then in the next cycle something should not happen, that is a safety situation, right. So, for example, if two people are requesting green light from two sides, so this is request 1, this is request 2, and green light happening is acknowledgement 1 and this green light happening is acknowledgement 2. What we are saying that acknowledgement 1 and acknowledgement 2 both should not be true at the same time. So, you probably want to create not A1 A2 A1 and A2, or you want to say A1 implies not A2, same thing you have to say A2 implies not A1, and any resource constant system we do same kind of modeling. So, that is the safety. Liveness basically means, so in this particular case G is always, G basically means always. So, always if certain event happens, then at some point somebody else will become true, right. If a car is waiting, eventually light will become green, eventually meaning how long later it does not matter, right. I mean in real world it does matter, you do not want to wait there indefinitely. Similarly, you have the concurrency, reachability and all that stuff. So, reachability, think about if you send a request, eventually you will get an acknowledgement that way, or in a structure like a graph, reachability basically means if I am in a particular, actually it is not, if I am in a particular state and is this state reachable. If you do not implement the FSM correctly, if the computation is wrong, then I may not be able to withdraw money. Withdrawing money is a state, somebody entering it is a state. If you did not implement it correctly, maybe there is no valid transition to go to withdraw money. So, that is a flawed design. So, that is basically reachability story. If certain state is not reachable, you make sure that from implementation you remove it, because what is the point of having a state that is not reachable, and attacker will sit there and hide. So, similar kind of template, once you have the template, I need to erase it. So, once you have the template, I wanted to show you for TDX, SGX or any example how the exact properties look like when you generate it. So, exact properties would look like, of course, this is how many properties and all that. So, remember the FSM1 we said TD life cycle and FSM2 was key management. In FSM1 state, if it is the ID is assigned to this particular process, that implies in the next cycle the key should be configured until transition is created. So, this basically means, sorry, my apology, key should not be configured until transition is created. So, until you created the page, the key should not be configured for that one to do any kind of valid operation. So, in liveness, if it is assigned and transition is config, then it implies that key is actually configured. So, similarly different kind of confidentiality and integrity properties are generated. Now, how do people verify results for us if you are not able to break, if you can break any of them, then your next thing is to contact two ways you do. You have a reporting obligation before you publish to the company. You send them an email or their security group saying that I found a vulnerability, and then they will come back to you saying oh, that is not a vulnerability, that is already known, mitigation exists, or they come back saying we will investigate, please do not publish next 6 months, 1 year and whatever. So, they come back. In parallel, you contact the NIST or the cv.org website, they have a protocol where you kind of file that and create the CV process. It can happen in parallel, or the company, once they agree this is a vulnerability not known, they will contact the Mitre Corporation and vulnerability will get created. It can create it either way. So, that is one way of producing results if you want to publish. Other way to go about it is basically talking about the kind of properties you generated, how good are those. So, for this particular scenario, the way we looked at it is that all these properties, what kind of coverage does it give, what kind of coverage does it give to the kind of API application program interfaces, all those APIs that exist. Recall this trusted execution environment. Trusted execution environment is basically provides interactions between different components and parties, hardware, virtual machine monitor, then on top of this VM1 and VM2. So, the way at least for Intel TDX is implemented, many of these are implemented as a either application program interface call, API call, or application in case of firmware application binary interface ABI call, does not matter, it is basically function call. So, there is a tons of function, how much of coverage you can give to some of those functions that kind of indicate this property, how much of the design it covers. It does not give any guarantee of correctness. If this coverage was really small 5%, 2%, that basically means most of the functionality or code these properties did not execute or exercise. Any questions?
This kind of property you check in simulation, right, or not in?
This we checked in Intel TDX simulation. That's the
but
only
the
code
Verilog
available.
code is not available with you, right? Then how do you?
If it is not available, then only option you have is to run on the real hardware.
Do you have availability of this?
The Intel TDX C implementation is available open source.
It's open source.
It's open source.
And how do you determine the property? Just analyzing the spec or the code, how do you basically identify this property?
In this particular case, later I will talk about the theorem and theorem proving. In this particular case, we came up with template and we are generating the properties which would look like this to cover different parts of the finite state machine. But in reality, if you change the template, a different property can be generated, but your objective is to kind of cover the whole finite state machine or the security subsystem. All possible way they will interact with each other, you want to make sure those interactions does not create to vulnerable scenarios.
So, how many FSM are there? It's single FSM or multiple FSM?
There are hundreds of FSMs, there are lots of FSMs.
So, you actually do composition of them or how do?
We actually do decomposition of them. Ideally, we should have considered all of them, but all of them is too much for the backend formal solution tools to handle. We are basically doing decomposition. We are just talking about when page table is talking to VMM, just that part. When VMM is talking to a VM, one virtual machine is talking to the VMM, just that part. We are just dividing and who is talking to whom, those conversations we are just trying to check, or the interactions of FSM in that space. So, now we are, so basically for the threat model for the TDX, only thing trusted, as I said the earlier diagram I said different components are trusted and non-trusted depending on whose solution you are using. If you are using TDX solution, the assumption is the hardware, processor hardware is assumed to be trusted, and tomorrow I will in the next lecture the tomorrow's thing I will even break that assumption, and the trust domain module, that one is trusted, everything else is, as you can see, BIOS is untrusted, VMM is untrusted, host operating system which is VMM untrusted, peripheral untrusted, any software that is not running on the TD is also untrusted. So, those are untrusted applications. So, everybody pretty much is untrusted except these two modules. So, if you do that, then how do you kind of verify? So, there are two ways you can go about it. One is static analysis, which I briefly talked earlier, I will zoom in now. Static analysis basically means trusted execution environment code is also any software code. So, the software the vulnerability requirement that you impose on any software, you want to do that for this one also. Then there are thing of invariant analysis. So, the invariant basically means something that should hold true forever. And if you recall, when we talked about assertion generation by Goldmine, they keep on running millions of tests and keep on looking the output and try to figure out, are there any relationship between those outputs. Is it happening when he is printing, whenever A is true, B is also true, when A is false, B is false. So, if try to find the invariant. So, because it is an English document, this invariant analysis has to be manual until one of you figure out a way a large language model can figure out in the document certain relationship that kind of manually we are doing right now, right. And no matter whether you generate through static analysis or invariant analysis, whether they are manual or automatic, eventually it leads to a list of properties or behavior you need to check. And because you are trying to do formal verification now, and this implementation we may or may not be able to exactly, then we may need to do abstraction. Then you take the property abstracted model and verify those properties. So, when you do invariant analysis, if I zoom into this particular module, when you do invariant analysis, so basically first you have to understand that what invariant are you looking for. In a Goldmine example I talked about, for classical assertions, we basically look for any functionality. Here if you are thinking of memory confidentiality, then you kind of need to figure out which components are more relevant or which interactions are relevant. If you are thinking of memory integrity, so then which particular components are important or which description I need to look at, and then I kind of generate invariant. They may be for firmware, maybe for hardware, maybe hardware plus firmware, it could be a combination of that. So, let me show you how an invariant looks like. First of all, for any invariant, before we write it in a temporal logic, it needs to make sense in English. TE should not allow an active private host key ID to two different IDs. So, that basically means if you are taking an exam for joint entrance, two of the registration numbers should not be same, right. If you are given a seat assignment in a flight, two people should not get the same seat. Same analogy here. Remember, anybody, any application, when they register, they get a HKID, and we are focusing on active. If some application just decided I do not want to be part of your story or part of trusted execution environment, gone, and that HKID is reused, that is perfectly fine. It is saying two people in the system, in the trust domain, should not have same ID. Now, once you write it, it basically little lengthy and complicated, that is why the manual part, because you need to look at the code. Code implemented all of these functions, they have their specific names for variable, you need to find those names. So, that's why HKDI info 0 and global data blah blah, then basically something has to happen. So, it is basically saying if it is there for one of them, for the other one it should not be the true, HKID should not be assigned for the second one, right. So, this part you do not need to focus. The important part in invariant I want you to focus is what behavior is expected. I have a laundry list, but it is not important, I can go for another one. T should not allow reassign private HKID when plain text data is still in the CPU cache for that HKID. Now, that particular program might have gone, but to avoid cache timing attack, any information that is already in the system, you do not give it HKID to somebody, that party will quickly come in and does not even have to do cache timing attack. It will access legitimately those addresses because it belongs to them. A second party comes in and claims as the first party, any remnant left by the first party, this party could be able to claim. So, that is a behavior, and again that could be kind of using the variables in the programs or the implementation, you will be able to do the invariant. There are many examples. So, it should be impossible for any software device which is not a TD to use the private HKID value. So, this basically means if somebody is not in the trust domain, did not register in the trust domain, remember the picture I drawn, you have hardware, you have you have hardware, what happened, this is pen. If you have hardware and on top of it you have the trusted part and you have untrusted part. So, this one basically saying somebody in the untrusted part should not be trying to from here or there or anywhere the HKID values, which is basically us versus them, that ID should not be assigned to them. So, there are many such things which I am going to skip, but in terms of verification, when you want to verify, you want to make sure. So, what are the things we want to look into this for this verification, and these are these implementation for TDX is available in SC code, and CBMC, if you recall bounded model checking we talked about earlier. So, this is a bounded model checker that works for with the C programs. So, then that program already comes with a SMT solver. So, that with the SMT solver, bounded model checking with the SMT solver, your objective is to kind of get the design, get the property and make sure it works correctly in a reasonable time and memory requirement. You can finish in a reasonable time. What you will observe for the hardware, we basically say not available, because at that point the TDX hardware was not available in the market, or we did not buy, whichever is. So, that is why none of the properties that were completely hardware property you could not check it, because we did not have the hardware. Now, the static analysis I talked about, the static analysis story, basically if you think about in this story, the anything you look here, all of them are specific to any software, but because we know in common vulnerability database, common vulnerability enumeration, buffer overflow is one of the top 5, and null and valid pointer, this pointer allocation, this is one of the top 5, memory allocation I do not recall, but either way these are the kind of vulnerabilities most attacks basically exploit. Given that this is also a code, you kind of wanted to figure out whether this exists. And the way kind of properties you look, of course, this property does not look like confidentiality, integrity, they look like buffer issues. If input length greater than 0 and input length like size of the buffer and something of that nature whenever you are computing anything. And this null pointer should not be null, as simple as that. Property 3 is valid pointer, which is basically pointer, and if you recall this particular one is exactly same as assert file pointer. When you open a file pointer, we do not want it to be null, that is exactly same as that. Only difference between these two is these should be checked statically to guarantee that design, this particular problem will never happen. In contrast, this particular one would be embedded into the program. During execution, if any time problem happen, this would fail and show it to you. If you ran for 2 million clock cycle, it did not fail, that does not guarantee the design is right. Only thing it guarantees, for the time it was running, there was no failure. So, formal verification of a property is a stronger guarantee than putting an assertion. Any questions? Would there be a break or we continue? Okay. So, if you look at the data set, when we ran, remember these are the all these API, if you look at the name, this is a page add, page augmentation, page demote, page promote, many of them are kind of these are page related, these are memory related, this is related to flashing, flashing done, this is related to key configuration. So, different aspects, these functions or these calls maintains different aspects of trusted execution environment. These are the bread and butter of those finite state machine implementation.
This is from your the C implementation of TDX?
From the C implementation of Intel TDX. These are available online, I mean publicly these are available. So, what we wanted to show that the static analysis of the properties we generated, that is reasonably good enough to kind of. So, it shows couple of things, how much of coverage it does on those programs, how much time it takes, reasonable time, but important part is these has so much of vulnerability. Now, having a buffer overflow vulnerability does not necessarily mean it is a serious problem, but it probably should be fixed or looked by somebody, because if this is a code of the trusted execution environment, that code should not have these kind of vulnerabilities, right. So, that is why whether trusted execution environment or any code, you want to just make sure that code is safe and trustworthy. So, now I am going to, now that we talked about decomposition analysis and property generation, we are going to talk about property checking.
So, the previous results is on CVMC, you run those
This is on
property
CVMC.
and on that C code.
CVMC using this kind of properties that is, so by the way these properties are kind of automatically generated by, so there is a static analysis tool exists that actually automatically generated. Once you kind of tick mark in that tool what issues you want to check, so they will generate all these properties for the design.
Which tool is that?
I need to go back and look at the paper. So, that tool actually exists to do some kind of linting software, it actually checks and generates all these kind of properties automatically. In contrast, for the trusted execution environment, the invariant analysis and all that we created manually until one of you can come up with large language models to do that generation from the specification. Now, in terms of property checking, I want to kind of zoom into some of these properties, and of course, lot of things can be done, community has done lot of stuff, I won't even spend time. So, whether you do design decomposition, property checking, bounded model checking, satisfiability, machine learning, there are many kind of choices there. So, I am going to take the example of very simple kind of, so this invariant and static analysis I kind of talked about how do they look. And the CBMC tool, the way it works, it actually whatever properties you create, you have to embed them as an assertion in the design. It may look like assertion, but the way SAT solver works, this is little bit of confusion because all along I talked about assertion is only checked during simulation, but the way these solvers work, this theorem prover and all that, they accept properties in this format. It just happened to be the name happened to be assert. And in this format when you give it, they mathematically guarantee for eternity. So, this is not a standard definition, but is think of a tool specific way of writing your property. So, let me kind of go straight to the so basically now we are going to talk about theorem proving, and we are trying to prove the theorem of let us say confidentiality theorem on Intel TDX. Before we do that, we need to kind of understand what exactly we are trying to prove, and mathematically I wrote it, I am going to skip that. So, conceptually if you have two kind of virtual machine and same attacker with different states or state transition, the attacker is trying to observe whatever observation is trying to make on two execution sequences or two traces, and if you compare the observation they should be equal. So, the idea of confidentiality basically means you try different ways of looking at things, you are not going to get extra information, you are only going to get information that publicly observable no matter how you try. So, that is basically this one. Integrity basically means you have the same virtual machine situation, but you are trying to do different types of attack, A1 on this one and same virtual machine A2 a different type of attack, but the observation you do the output is still the same. So, you are not able to alter anything. So, that is basically the integrity. Now, these equations are important because this is exactly this we will convert it to assertion and we will put it that to that theorem prover. And this is being so complicated, we broke it into different parts and I will show you bits and pieces. Any question on this mathematical formulation or when you want to go for theorem proving route of any of these to kind of guarantee that, of course, assumption is the way we formulated the problem, this formulation the theorem is correct. If theorem is wrong, then theorem proving is meaningless. So, if theorem is correct or our formulation of the problem what confidentiality means, if that is correct, then you run it on the trusted execution environment software and then you basically check it holds. Same thing for integrity. So, again confidentiality means nobody else should be able to see it or understand it, integrity means nobody will be able to alter anything in it. Okay. So, how do you, if you want to go for such a verification, how do you go about it? So, this one basically you have to implement the formal model of all the designs. What language was it? This is one of the formal languages. So, basically you model the design as well as all the table, data structure, everything you kind of model in that language. And then once you are done modeling the different types of tagged cache, TD owner bit, everything you have to implement. And if you have used Lisp programming language, it is similar to kind of Lisp based implementation. So, once you do that, then basically you will be able to run your experiments, and in this particular case, so confidentiality property, when we say 10, so this particular integrity 3 and how long it takes for the TDX and all that, it basically means, let me go back to, so basically means this particular computation needed to us to compose them as different checking and ending of those, that is what it basically means. And so, the key idea is that we can actually verify this in a reasonable time, and we kind of guarantee that if you check that property, it is kind of do whatever it is supposed to do. So, any question? So, this is on Intel TDX, there are a lot of work people are doing, and in fact, Google have published multiple white papers on, they invested lot of their engineers, a lot of years in trying to verify all the trusted execution environment along with the engineers of that company. Unlike us or you and me, when you do research, nobody works with us, but when Google did that evaluation, Google and Intel TDX team worked together. Same thing for AMD team and Google worked together. So, they kind of produced a laundry list of huge publication to show what kind of, so they first of all they found many vulnerabilities, and that the companies eventually fixed. Then they also showed what kind of test cases do you want to run. If you are building a new trusted execution environment, what would be a standard kind of test? When I talk about cryptography later tomorrow, I will talk about that. Google have a Witchy proof project, they also developed a suite of test cases. If you are developing any cryptographic modules or function, you better run those test cases before you release it to anywhere or use them. So, similarly for trusted execution environment, they kind of created a simulation based validation framework, which does not give you any guarantee. That is why we pursued this path, that how can you give some formal guarantees on some stuff. Any question on verification of general purpose T? So, anything I talked about, these are general purpose TDX, it can be used any desktop, laptop or anywhere. Now, I am going to talk about a small snippet of it, but applying to embedded kind of T. T is in embedded environment. And this particular work builds on what Dr. Karfa kind of talked on sidechain analysis, but only thing I want to show, even in embedded environment where resources are scarce, they still support all of this stuff, and I am going to just zoom in. Of course, most of them uses either ARM core or RISC-V based core, and we decided to go for RISC-V based implementation because all of these are open source. We can actually run on the hardware everything. The implementation of the trusted execution environment, the virtual machine, the kernel, everything is available, whole stack is publicly available. You can run all of it. So, at the bottom, as you can see, you have hardware, RISC-V core. So, root of trust, just think of those cryptographic modules that I will zoom in tomorrow. And then on top of it, they operate in different mode. This is the security kernel mode, which is trustworthy, lot of drivers and lot of untrusted app, that could be some trusted app. And even in the memory, there are different memory region that are partitioned as this memory region is trusted, this is untrusted. So, roughly speaking, if you match the color, this memory region, when operating system allocates, this memory region will be only allocated to trusted apps. But it is not that anybody can use any part of the memory, you will still have partition. If trusted app is two program, this one will be divided in two parts, or maybe two program, one program will use only this part, another program will use only this part. So, those standard definitions still apply. So, this is basically the overall view of how the TE architecture looks like. Now, the attack that I wanted to show is based on the idea of operating system, and the operating system we kind of covered little bit, let me do little bit. So, I wanted to show something about context switching and then I will come back to this slide. So, one of along with lot of work operating system does, one of the work it does is context switching or task management. So, operating system, in the morning I talked about the memory management of the operating system maintains a table or called process table, and in that table it maintains lot of information including the name of the process P1, P2, P3 along with all the relevant information also known as context. Just for the sake of argument, let us assume the program counter value where it is supposed to start if it has not started yet, or program counter value where it is supposed to resume if it has executed little bit. Now, so let us say this could be program counter value of 128 and this one could be program counter value of 1024 and this may be the beginning, this may be the start and this might have executed, this may be somewhere in the middle, right. It maintains all of that. In addition to that, it does scheduling. Who will execute now? Lot of processes are ready for execution. If there is a priority, let us say P1 has higher priority, then P1 will continue. Maybe P2 was working here and at 1023 or 24, this guy decided to start at program counter value of this PC equal to 1024. This process the operating system decided that I need to start program P1, then it sets the program counter value to 128 and then processor executes, because processor does not understand any of these. Processor job is to whatever is in the program counter, it will keep fetching from there to keep on executing, right. Now, while this is happening, if this is not the end of program 2, program 2 is going to come back. When program 1 is done, then that basically at that point program 2 needs to come back and it need to start with PC equal to 1024. But at this point operating system has to do few things, because in your processor if you think about, you have the CPU, you also have registers, it could be R0 all the way to R31. You also have many other things, translation, look aside buffer, little bit of memory controller information, but just let us focus on this, just program counter and this register. So, this is the context that need to be saved, right, something of that nature, or any variables it modified, those value need to be saved. Something need to be saved, so that the program when it starts here, it starts at the right place. If this did not happen, wherever the way it continued, it should be almost the same, except that it is understood that earlier cache had lot of useful data, now many of them probably got kicked out, because this process when it started, or this program when it started bringing its own data and cache has little space, is going to throw and kick out data for the another process. So, that loss will happen, that is known, but apart from that some of the stuff needs to be saved. So, context switching basically means we have to save this. Let me ask a question now, how do operating system saves this? Where does it save? We understood this needs to come back, we want to start exactly where we stopped. Where would it save all these values? Main memory. How does it save? What instruction do we have? Does operating system have space? What system call? No, all of these are stored as store instruction, whatever the store instruction is, store word, whatever. The load store is uses the same instruction, there is no operating system special instruction, it uses store instruction for all the registers. So, store R0 whatever address is supposed to go, let us say address, I need some space, let us just write it here, let us say store R0 and location 100, store R1 in location 104, store R31 in location I do not know 32 multiplied by 4 some 1100 some number, right. So, whatever that number is, you store all of them, you saved the context. So, this is what does at this point. At this point you need to bring the data. How does it bring the data? It needs equal number of load instruction. All these store now exactly same address, you would be loading R0 from 100, it would be bunch of load instruction from the same addresses. Now, in reality this is a lot more optimized. If some register has not been modified, then you do not want to write it. R0 is always 0, you do not want to write it. There are a lot of optimization, but that is besides the point. The point is whatever the context needed for it to start execution, you need to save as a store, you need to load as a load instruction. This is context switching overhead. It does many more things, but this is the bare minimum, right. So, now I can go back and talk about it. So, the question on this attack, this particular attack is that can we use this feature of storing and saving, and can we break the trusted execution environment. And what we are showing is I am showing you only two programs, one is the untrusted program, one is the trusted program. Now, when operating system switches from untrusted to trusted, there is a saving to memory. When it changes from this one, it is from again saving and storing, is saving the context of this program, loading the context of the other program. These load and store, can we differentiate from normal operation? And answer is yes. If you look at this kind of power traces, this is basically, so in as you recall the discussion earlier by Dr. Kaur, for that the first important point in side channel power side channel attack, can you identify boundaries, which execution is beginning when and ending when. Once you identify the boundaries, then from these values can you figure out what those values are. Ideally you want to find the secret or the key value, but even if that is not the case, even if we find the register values, that is still an attack, program counter, register, whatever value, because that value you can use to further do the attack. Now, the reason this looks this nice, life is normally not this nice, because RISC-V, the version that is available online, it does not do any optimizations. If you try to do this for any of the existing hardware, Intel, IBM, AMD, you are not going to get such a beautiful one, because the RISC-V always saves all the registers and exactly saves in that order. If it changes the order, do some trick, you will not find such a beautiful thing. It is exactly R0 to R31 load, R0 to R31, sorry, R0 to R31 store followed by R0 to R31 load. And once you are able to have that, then you kind of course, you can still kind of do efficient test generation to generate better power profile, and then once you trace analysis, you are trying to figure out, did I found the values. So, we kind of did an experiment in all possible scenarios. The reason I say all possible, when we published last year, there are 4 SOC available, system on chip, that are available publicly. On all 4 SOC, there are exactly 4 trusted execution environment available: Keystone, OpenMZ, Komodo and Saticos. We wanted to do all 16 combinations of them and see how many of them we can break. And because of the nature, the way they are not, did not optimize the context switch, the context switch code is exactly linear and simple. Actually, we are able to break all of them. So, without getting into the detail, in side channel attack community, we have the notion of alpha, and if the value is kind of below the alpha, then you have a statistical guarantee that you can find the value, 100% guarantee. If it is above the alpha, then you need to do little more experiments. What I wanted to highlight, these 16 combination, 4 system on chip board, remember this is running the full thing, unlike the TDX and SGX, we are just taking a little subsystem and trying to prove. This we take the whole board, whole thing running on a board, all the 4 operating system or whatever you call it, trusted execution environment loaded. So, this is Pico SOC with all 4 OS, this is UARV SOC, this is IOB SOC, this is VRWolf, all 4 open source SOC, all 4 running. We can see from register 8 to register 31, we can find out their values. With the 0 to 7, 0 to 7 it was tricky, and maybe further analysis was needed. One of the reason is RISC-V uses R0 to R7 for very weird reason, many kind of like stack pointer, frame pointer, they are not kind of regular behavior, they are kind of slightly weird. I am not even suggesting we can't hack those, but at least more experiment, more analysis needed, but these we are able to find for all of them. And the mitigation is obvious, mitigation is do not have context switching code from R0 to R31 exactly in that order. So, if you kind of switch, swap or optimize or randomly kind of write, because eventually you are writing to the same address. So, just change that random, then all that beautiful structure will go away, this beautiful structure will go away. So, first of all identifying boundary is one thing, second thing identify which one belongs to R0, which one belongs to R1. Right now it is kind of linearly kind of done, we exactly know first one is R0, then R1, then R2, we still have to find the boundary for them, but you kind of divide it into 64 pieces. We divide in 64 pieces, then analysis become trivial and easy. But if every time if it gets randomized when it writes or any other optimization happen, then it is not going to be trivial the way we are able to do.
So, so this your RISC-V is the processor, right?
RISC-V.
And in SOC, what are the other things? So, you saw the experiment for 4 different
So,
SOC, right?
so this SOC, I am only showing this stuff. So, basically what is this PMA? You pretty much have your cryptographic modules, you have your RISC-V core, then you have your operating system, then you have the applications running and few controller and converter, whatever the simple boards comes with, like
So that
6
is in
or 8 components.
FPGA board or?
No, the release version has the code, you map it to FPGA board. The release version is just the code, you have the full code base.
You have the Verilog code for the entire SOC?
For entire thing, Verilog code, operating system, software code, firmware, everything is available online.
Physical boards are also available. Physical board also.
Physical board, I mean they also comes with readme what board they tested on it, then you have to get that board and then you map it, so it is going to work on that board. And then you measure on that board, those powers are measured on basically those boards.
So when we are getting 1500 rupees, you will get actually RISC-V board in India.
Those boards are very cheap.
Very cheap, 1500 rupees you will get.
But can you measure power on that?
Yeah.
All you need a resistance, somebody embedded the resistance in that board and you measure across that resistance, and that is the only 1 or 2 application running and you are going to get accurate.
They have this RISC-V board, and in India many companies are making this board.
That is pretty much all I have. Thank you, have a nice day.